When I first saw this king bill, I noticed that the eyes were able to track the player, and I wanted to recreate that for an enemy in my game, the Chomper. But it proved to be more difficult than I first thought, and one specific math function helped save the entire design. It all began with one question. How would you get the eyes to actually follow the player? Well, it becomes much simpler when you break down the logic of it. If we want the eyes to track the player, then what we really want is the angle between the eye and the player. With our knowledge on degrees, we could try calculating this angle with sine, cosine, or tangent. Or more specifically, by using inverse trig functions. Normally, the trig functions of an angle will provide the ratio of its respective lengths. For a sine function, that would be the ratio of the opposite side of a given angle over the hypotenuse. But inverse trigonometry would work the exact opposite. If we supply the ratio of the opposite side over the hypotenuse into an inverse sine function, we would actually get the angle. When it comes to eye tracking, arctan would usually be the best option. That's because for arcsine and arccosine, we would have to calculate the diagonal distance between the player and the enemy for the hypotenuse. But that's just too much work. However, using arctan to find the angle has one major limitation: its bounds. Arctan has an output of radians, which is a unit of measurement that measures angles in terms of pi. Normally, I would have a corny addendum saying something like, no, not that pi, I mean the irrational constant equal to 3.141592, but that seems too forced, so I'm not going to make that joke. In any case, if we were to graph arctan, you would notice that its range is limited at negative pi over 2 and pi over 2. In degrees, that would translate to negative 90 and 90 degrees respectively. So why exactly is that a problem? To better explain this, let's go back to the Chomper. You can see at some point that the eyes will abruptly flip because the angle needed at that specific point is outside the range that we discussed earlier, from negative pi over 2 to pi over 2. Specifically, if we look at a coordinate plane, opposing quadrants will have the same angle. If we take the point 5, 5 and try finding the angle for arctan, we'll end up with pi over 4 radians, or 45 degrees. But let's say we take the point negative 5, negative 5 in the opposite quadrant. Then we'll have arctan negative 5 divided by negative 5, and the negatives cancel out, meaning we'll have pi over 4, which is exactly the same as before. Because of this, arctan thinks that angles that are in quadrant 2 and quadrant 3 are the same ones as quadrant 1 and quadrant 4. While technically correct, for the Chomper that means the eye tracking will not work. It'll ignore half the angles that we actually need. Does that mean that the eye tracking design would fail? I mean, of course not, otherwise the video's runtime would be way over by now. And that's where this one special function appeared, arctan2. You see, arctan2 actually has the range needed for everything to work. From negative pi to pi radians, or 0 to 360 degrees, it can cover the entire circle. This means that any angle can be produced from arctan2, effectively fixing the entire design. But in any case, how exactly does arctan2 work? It's functionally similar to a bunch of different arctans, but with different conditions. So if arctan2 is a bunch of arctans, how come it can actually cover the entire circle, whereas the normal arctan can't? To explain this, you have to keep in mind that arctan2 actually has a different argument order. For the normal arctan, you need to put the ratio of the opposite side over the adjacent side of the angle, or more specifically, y over x. But that results in arctan messing up the direction in quadrant 2 and quadrant 3. With arctan2, however, you have to input y and then x. And that allows arctan2 to keep track of the signs of x and y for conditional arctans. So again, what exactly are conditional arctans? Imagine that we could tell which quadrant an angle was in, and then adjust the results of an arctangent function based on that. Well, because we can keep track of the signs for x and y, we can. For an angle to be in quadrant 1 or quadrant 4, the only real condition is that x needs to be greater than 0. If you recall, quadrant 1 and quadrant 4 are perfectly safe for arctan to work for, because that is in the bounds of negative pi over 2 to pi over 2 radians. But what happens if x is less than 0, in quadrant 2 and quadrant 3? In that case, it depends if y is greater than or equal to 0, or less than 0. For the first case, that means that the angle is going to be in quadrant 2. But again, arctan's range is restricted there. So to fix that, we can take the result of the arctan and then add in an extra pi, not that one, to get a result in quadrant 2. If y is less than 0, that means the angle is going to be in quadrant 3 instead. But in this case, we can take the result of arctan and then subtract pi to get a result in quadrant 3. And that allows arctan 2 to cover all 4 quadrants. However, there is another thing that arctan 2 does that is great. I've mentioned cases where x is less than or greater than 0. But what if x is 0? If we think back to arctan, the argument itself is y over x. But that means if x is 0, arctan is undefined. When that's the case, what about a 90 or negative 90 degree angle? Fortunately, arctan 2 has a great solution for this. There are 2 cases for when x is equal to 0. If y is greater than 0, then it's going to return pi over 2 radians, or 90 degrees. If y is less than 0, then it returns negative pi over 2, or negative 90 degrees. That being said, arctan 2 will be undefined if both x and y are 0, since that would be the origin and you can't really calculate the angle at that point. However, with these conditional arctangents, arctan 2 is able to function perfectly and fix the Chomper's eye movements. In any case, math itself can seem boring a lot of the time. You might question, why would I ever need to use this, or what's the point in even learning this? Which, don't get me wrong, I think those are important questions to ask. But personally, I think it's important to learn and discover as many things as you possibly can. You never know when it might come in handy, even for something as niche as fixing eye movement for an enemy. Speaking of eye movement, your eye should be angled towards that subscribe button. Maybe, potentially, I'm only kidding. Thanks for watching.